Hello, science fans. So, look around you. Our world is filled with amazing gadgets. We have smartphones that fit in our pockets and smartwatches that track our steps. But, what powers all this cool technology? Batteries. For a long time, batteries have been like little hard bricks. They are stiff, they are solid, and honestly, they don't like to bend. This has been fine for phones and laptops, which are also stiff and solid. But technology is changing. We are now imagining things like clothes that can monitor our health or screens that we can roll up like a piece of paper. These new ideas need a new kind of power source. The problem with our current batteries is simple. They are rigid. Think about a normal lithium-ion battery, the kind in your phone. Inside, it has layers of materials pressed very tightly together. These layers, called electrodes, are where the magic happens. They store and release energy. But these electrodes are often made of a thin metal foil, like aluminum or copper, coated with a brittle, powdery material. If you try to bend this, what happens? Crack. The coating can flake off the foil, creating tiny gaps. This is a big problem. These gaps stop the flow of electricity, and the battery can lose its ability to hold a charge, or even stop working completely. Imagine trying to fold a cracker. It just breaks into pieces, right? That's what happens inside a regular battery when it's bent. The delicate internal structure just can't handle the stress. This damage is permanent and can even be dangerous, potentially causing the battery to short circuit. So, for our future of wearable gadgets and flexible electronics to become a reality, we need to completely rethink how we build batteries. We need them to be as flexible as the devices they power. We need batteries that can twist, bend, and fold without breaking a sweat, or more accurately, without breaking their internal connections. This is where the science gets really exciting. Scientists and engineers all over the world are working on this very problem. They are inventing new materials and new ways to put batteries together. Their goal is to create batteries that are not only powerful, but also incredibly flexible. Imagine a battery that feels more like a piece of rubber or a strip of fabric than a hard block of metal. This isn't science fiction. It's the future of energy storage. These new flexible batteries will unlock a whole new world of possibilities for technology that we can wear, carry, and even fold up. It's a revolution in power. To make a battery bendy, we need to change its recipe. We have to swap out those stiff, brittle ingredients for something new and flexible. One of the most promising ideas is using flexible carbon materials. Think of carbon not just as the black stuff in a pencil, but as a super versatile building block. We can arrange carbon atoms in special ways to create materials that are strong, lightweight, and can conduct electricity, all while being able to bend. Instead of a stiff metal foil, we could use a fabric woven from carbon fibers. This creates a base that is naturally flexible from the start, like a piece of cloth. Another amazing group of materials is called conductive polymers. The word polymer might sound complicated, but it just means a material made of long, repeating chains of molecules. Plastics are polymers. Normally, plastics don't conduct electricity. They are insulators. That's why we wrap electrical wires in plastic. But conductive polymers are special. They are plastics that can carry an electrical current. Imagine a battery electrode that has the flexibility of plastic wrap, but the electrical properties of a metal. These materials can be bent and stretched over and over again without breaking, making them perfect for our bendy battery needs. Then there's a super cool material called MXene, pronounced Max-ene. This is a relatively new discovery, and it's making a big splash in the world of materials science. MXenes are like incredibly thin, two-dimensional sheets, almost like atomic-level pieces of paper. What makes them so special is that they are highly conductive, like a metal, but they can be mixed into a sort of ink or paste. You can then paint this MXene ink onto a flexible surface, creating an electrode that is both paper-thin and highly efficient at storing energy. It's like having the power of a metal in the form of a flexible, paintable liquid. Each of these strategies offers a different way to solve the same puzzle: how to make an electrode that moves without breaking. Some researchers are even combining these ideas. They might mix conductive polymers with carbon materials to get the best of both worlds. The goal is to create a structure that allows the energy-storing particles to stay connected even when the whole battery is being twisted and turned. It's like building a road out of rubber instead of concrete. The cars or the electricity can still drive on it, but now the road can bend and flex with the landscape. Let's zoom in on one part of the battery, the anode. This is the electrode where lithium ions are stored when the battery is charging. To make a flexible anode, scientists are turning to some superstar forms of carbon. One of these is carbon nanofibers. Imagine microscopic threads of pure carbon, thousands of times thinner than a human hair. Scientists can weave these tiny fibers together to create a mat that looks and feels like a piece of black felt. This felt is not only flexible but also has a huge amount of surface area, which means it can store a lot of lithium ions, giving the battery a good capacity. Another carbon hero is the carbon nanotube. These are even smaller than nanofibers. They are tiny, hollow tubes of carbon atoms arranged in a hexagonal pattern. Think of them as rolled-up sheets of graphene. Carbon nanotubes are incredibly strong, lightweight, and fantastic at conducting electricity. When used in an anode, they can create a tangled web-like network. This network acts like flexible wiring, holding the energy-storing material together while allowing the whole structure to bend easily. The electricity can find many paths through the web, so even if one connection breaks, the power keeps flowing. It's a brilliant way to build in resilience. And then there is graphene, the wonder material. Graphene is a single, flat sheet of carbon atoms, just one atom thick. It's the strongest material ever tested. It's almost transparent, and it conducts electricity better than copper. By layering these atom-thin sheets, we can build an anode that is extremely thin and flexible. The problem is that making large, perfect sheets of graphene is still very expensive and difficult. Another challenge for all these carbon materials is making sure they stick well to the other battery components. Sometimes, the bond between the flexible anode and the other layers can weaken over time, which hurts the battery's performance. So, while these carbon superstars are amazing, they are not perfect yet. The cost of producing high-quality carbon nanotubes and graphene can be a major hurdle to making these batteries affordable for everyone. Scientists are also working hard to solve the bonding problem, ensuring all the flexible layers of the battery stay stuck together like a well-made sandwich, even after thousands of bends. But the potential is huge. These materials are paving the way for anodes that are tough, efficient, and ready to be part of the next generation of flexible devices. The science is moving fast, and these challenges are being tackled one by one. So, we have these new flexible batteries. How do we know they actually work? Well, we have to test them, of course. But we can't just use the old tests. Scientists have designed special machines that repeatedly bend, fold, and twist the batteries. One common test is a bending test, where a machine will bend a battery back and forth thousands of times to a specific angle. They might even fold it completely in half or wrap it around a cylinder, again and again. While the battery is being flexed, its performance, like its voltage and capacity, is constantly measured. The results are truly impressive. Many of these new flexible batteries can be bent thousands or even tens of thousands of times and still work almost perfectly. Imagine folding a piece of paper 10,000 times. It would be completely worn out. But these batteries can endure that kind of stress and still power a small light or a sensor. For example, a test might show a battery retaining over 90% of its original energy capacity after 5,000 bending cycles. This proves that the new flexible materials and structures are doing their job, keeping everything connected and the energy flowing smoothly. This incredible durability is what will make future technology possible. Think about smart clothing. A battery woven into the fabric of a shirt would need to survive being worn, stretched, and washed. Or consider a medical sensor that sticks to your skin like a bandage. It has to move with your body. Flexible batteries are the key to making these ideas practical. They will power everything from wearable health monitors that track your heart rate to foldable smartphones that you can tuck into a small pocket. The possibilities are as flexible as the batteries themselves. The future of electronics is not flat. It's dynamic, wearable, and integrated into our lives in ways we are just beginning to imagine. Hard, blocky batteries simply won't fit into this future. The development of flexible, reliable, and safe batteries is one of the most important steps toward this new technological era. We are on the verge of a power revolution, moving from rigid bricks of energy to soft, adaptable power sources. Thanks to the amazing science of materials like carbon and MXene, our gadgets will soon be able to bend, fold, and stretch right along with us. Consider that. The future is flexible.